Now let's start talking about magnetism. Magnetism first began many, many centuries ago with naturally occurring materials that were found to attract other materials, specifically metals. These were found in materials that today we call iodostone or magnetite, different materials that have this property. Now, an interesting fact is that these materials were, as far as our records show, were first discovered in a country in Middle Eastern area that was then called Magnesia, hence the root magnetite and magnetism. Now, what we found is that this attractive property is very, very similar to electricity, with positive charges attracting negative charges. But there are some fundamental differences, so we're going to call these different. Rather than positive and negative, we're going to call them north and south. The reason being that the north pole of a magnet is a north-seeking pole. In other words, it points towards the north, the northern region of the Earth, and the south pole tends to be attracted to the southern poles of the Earth. Now, there are lots of magnetic type of materials: iron, cobalt, nickel. These are what we call ferromagnets. Instead of permanent magnets, these are ferromagnets, meaning that they induce magnetic type properties when in the presence of other magnets. Now, fast forward a few generations, get into a modern view. What we have discovered is that a magnet does have a north and a south pole, but there is a field of influence. Just like there is an electric field of influence due to electric charges, there's a magnetic field of influence due to magnetic poles. So we call these magnetic fields. And these field lines are oriented so that they point from the North Pole around to the South Pole, as you can see here in this figure. Now, a couple of things that are fundamentally different between magnets and electric charges. With electric charges, you can separate a positive charge from a negative charge. They exist independently of one another. With magnetic fields and magnets, it is inseparable. If you try to separate a North Pole from the South Pole, then you're just going to get two magnets. Poles will always come in north-south pairs, always. And as we said, field lines go from North Pole to South Pole. Similar to electric charges, positives and negatives, electric charges attract, but like charges repel. Similarly, unlike poles attract, a north is attracted to a south pole, and a south pole is attracted to a north pole. But if you have a north pole next to a north pole, they will repel each other. So like magnetic poles repel, and unlike poles attract. Now, we talked a little bit about ferromagnetic materials, but let's talk a little bit more about what makes it magnetic and how we might have a permanent magnet. Basically, the magnetism depends on what we call the atomic magnetic moment. Now, moment is just a mathematical term to describe the property. Basically, what it means is it depends on the electron and proton configurations, the materials that make up protons and electrons. It also depends a lot on the orbital motion of the electrons themselves. Now, these moments basically have an orientation, and if these orientations are randomized, such as is in the top figure, then it's not magnetized. And generally what will happen is a group of atoms in a region will all align in the same direction. These are called domains. If each domain is randomly oriented, it is not magnetic. So, for instance, a piece of aluminum or a piece of plastic would have this property, and so it will never attract. But in the case of a ferromagnet, such as iron or copper, if if you induce a magnetic field around this ferromagnet, then the domains will realign so that for the majority, they are pointed in the same direction as the magnetic field. At that point, all of these atoms start working together and start exhibiting these magnetic properties, and it becomes a magnet. So that's a ferromagnet. If you were to remove this metal from the magnetic field, it would become randomized again and would no longer be magnetic. But to create a permanent magnet, basically what you need to do is take these domains and make them malleable somehow, induce them to a magnetic field, and then when it cools down, when it hardens, then you've got yourself a permanent magnet. So what happened with the magnetite in the country of Magnesia, likely what happened was there was a volcano, so you have, or some sort of a lava flow. You have lots of molten iron and other materials which show these magnetic properties, and as they flowed out into the surface, they were exposed to the magnetic field of the Earth. Then when the rocks hardened, they permanently exhibited all of these magnetic properties so that when it became not exposed to a magnetic field, the domain stayed aligned and it was a permanent magnet. Let's talk a little bit about the Earth's magnetic field since we just mentioned it. The source of the magnetic field has to do with the rotation of the molten core of the Earth. Now, the core of the Earth is made of a whole number of molecules and substances, but the primary material that the core of the Earth is made of is iron. And so that rotating iron generates some of these alignment properties, which creates a magnetic field around the Earth. Now, remember how we said that North poles are attracted to South poles and South poles to North poles? Well, if you suspend a magnet, you'll see the North pole being attracted to the northern region of the Earth. But if the North pole of a magnet is attracted to the northern region of the Earth, that means they have to be opposite poles, which means that the magnetic properties of the Earth shows that would have basically the southern pole of a magnet near our geographic North Pole, so that the North Pole of any magnet would be attracted to that southern property. So kind of an interesting little, how do I put it, an interesting concept that is very different from what logic dictates. Now, another problem is that the geographic North Pole may not align with the magnetic North Pole. In fact, it rarely ever does. The magnetic poles shift, and they progress from one point to another over time. But very, very, very rarely in the Earth's entire history have these two poles lined up. And so if you want to use a compass, which uses that magnetic property attracted to the magnetic North Pole, it's not going to point true north. So you're going to have what's called a magnetic declination. That's the difference between the geographic and magnetic poles. And that declination, or that difference in angle, was going to change depending on where you're located. Here's a map showing very typical standard magnetic declinations. Now, every once in a while, the magnetic field, the direction just completely reverses. So right now, the Earth's magnet has a North Pole in the southern region, South Pole in the northern region. That would completely flip. It happens every once in a while. And as a result, you generate lots of deposits of magnetized material. The last time this happened was about 780,000 years ago. And there are lots of studies trying to figure out what would happen if this happens again, and when is the next time that this is due, that a reversal will happen.